Hi everyone. In today's video, I'm going to be talking about how you can add a keyboard to any of your projects. Here I'm using an FPGA to decode signals coming from the keyboard directly from the keyboard plug by taking wires into the plug and reading what those values are. And the FPGA will then, when you hit a key, read in from the plug and figure out what key is being pressed. So the PS2, first of all, you might be wondering why we're using a PS2 keyboard. Here's the PS2 plug, instead of the USB-based keyboards, which are much more common today. And the reason is that PS2 is an older protocol that's been around since the 1980s, and as such, it's a much simpler protocol to deal with. In PS2, the plug has 6 pins: ground, power, data, and clock. So ground and power here are being powered by 0 volts and 5 volts, which comes from the FPGA. And the data and clock are being sent back from the keyboard and read into the FPGA through these input reading pins. And they're also, I connected the oscilloscope to the data and clock so that we can inspect what the keyboard is saying. So if I press different keys, you will see that the data changes. So let me turn off the clock. Clock is yellow, so it just goes up and down. If I turn off the clock, you can see that different keys that I press will have different data patterns. Okay, so I'm going to hit the key S. Let me turn clock back on. I'm going to hit the key S, and we are going to analyze this to figure out how we can go from reading in the PS2 clock and data pins into our FPGA or whatever hardware you're using, and decode that signal to figure out what key on the keyboard was pressed. Okay, so here's that image from the oscilloscope for where we just pressed S. And remember, the yellow is clock, okay, and the green is data. So let's look at when does clock go from 0 to 1. Well, it happens here. And at this point, the green is 0, so data is 0. In the next clock rise, data is 1. In the next clock rise, data is 1. In the next clock rise, data is 0. In the next clock rise, data is 1. Okay. This one, it's 1. This one, it's 0. This one, it's 0. This one, it's 0. This one, it's 1. And this one, it's 1. Okay, so that's our sequence. Here, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1. Okay, so what does this mean? Okay, so the first bit is called the start bit. It's always 0. The last bit is the end bit. It's always a 1. These 8 bits here are what represents what key was just pressed. So if you take these bits and you reverse them, and convert that to hex, okay, so base 16, you will get 1B. And this corresponds to what key was pressed. Here's a table of what each key on the keyboard corresponds to in hex, okay? This is called the PS2 ScanSet 2. You'll see that there's make and there's break. Make means when you first press down the key, this is the signal that's sent. Break means when you release the key, this signal is sent. So with the keyboard, first you hold down a key, then you release the key. And those are 2 separate events. And the break code is just the make code, except you have 2 of these 11-bit frames. The first one is the hex F0. Okay, and in case you were curious, this last bit here, well, this bit right before the end bit is called the parity bit. It's used for odd parity. So what this does is ensures that the number of ones within here is odd, okay? So you can see that we have 1, 2, 3, 4 ones. That's even. So in order to make it odd, this parity bit must be a 1. However, let's say that this were a 0, then there's already an odd number of ones, so this can be a 0, okay? So that's just to ensure that we got the right signal, because if the parity bit led to an even number of ones, then you'd know the signal must have gotten corrupted. That's not very important for us, but that's just good to know. Okay, so all we have to do, in conclusion, is check these 8 bits coming from the PS2 data and clock signals, and then that can be mapped to what key was pressed. Okay, so now that we've talked about the theory behind how a PS2 keyboard works, how it sends its signals through the PS2 clock and data pins, how do we take in the PS2 clock and data signals and have an FPGA read that and figure out which key was pressed? Well, let's talk about how to do that. So here we have a module in Verilog, which is going to take in the PS2 clock and data wires, and its job is to output a frame of 11 bits. So it's constructing that frame from the clock and data. And when it's done constructing the frame, it will make this new key variable B1, pulse 1 for 1 cycle. This is a finite state machine, and it starts off idle, and as soon as the PS2 clock falls from 1 to 0, which indicates the start of a key being pressed, then it will enter the saving input state. And in saving input state, it's going to have each one of these bits just plopped into, bit by bit, the 11-bit frame that it constructs. And once 11 bits have been constructed, then it will enter this third and last state called transmit key, which will then, in this state, new key will be true. Okay, it will be 1, so new key will pulse for 1 cycle, and PS2 frame in this state can be read in its full glory after 1 cycle, returning back to idle. So PS2 frame is being stored in a DFF, and so is the current read bit index. So the way it's going to work is we're going to have 11 zeros, right? Because when in idle, PS2 frame is going to start at 0, and read bit index is also going to start at 0. And when we're in saving input, the next value for the PS2 frame is going to be the current PS2 frame ORed with the PS2 data shifted over to the left by read bit index. Essentially, place PS2 data in the index, read bit index, within the PS2 frame. So if this is the PS2 frame, and we start off with read bit index all the way on the right, and PS2 data is a 1, then it's going to be this ORed with this, which is going to produce a next value of 1. At that point, the read bit index will increase. Say the read bit index is over here, and PS2 data is once again 1. Then the next PS2 value would be 0, 1, 1, 0. So as you can see, we are each time moving moving read bit index up 1 bit and inserting where read bit index is what the value of PS2 data is. All right, so now that I've talked about this diagram, let's talk about the code. So here's the Verilog implementation. We take in the clock and data, we output the frame. We also store the previous value of the PS2 clock signal by just delaying it by 1 clock cycle with this DFF, so that we can see when the clock is rising and when the clock is falling by comparing the current PS2 clock value with the previous value and seeing if it's a 0-1 or 1-0 relation. We are storing the state in a 1-hot encoded format in this DFF. The format is as follows. So each of the three states, idle, saving input, and transmit, has its own one hot encoding. And the next state is computed like so. By default, we are idle. When we are idle and we notice that the PS2 clock just fell, then we should enter saving input state. Let me pull the diagram to the right so that you can see what I'm talking about. When the PS2 clock is falling, which is indicated by the previous PS2 clock being a 1 and the current PS2 clock being a 0, and we're in idle state, we should go to saving input state. Okay, that's what happens. Also, when we're in the saving input state and the read bit index hits 11, we've just saved in 11 values into our frame. Now it's time to transmit that. We go to transmit. We're only in transmit for one cycle, so no matter what, when we're in transit, we are going to go back to idle on the next state. And then, of course, stay in your current state otherwise. And that's because, you know, for every single PS2 clock cycle, there's going to be like 10,000 or whatever clock cycles of the FPGA. So we need to stay in our current state while we're in the middle of saving an input. Now that we have the state, let's talk about the read bit index. Read bit index is going to increment by 1 only when we're in saving input state and the PS2 clock goes from a 0 to a 1. Okay, so when we're here, when the PS2 clock rises, like so, actually this is a better image. Every rise here, read bit index is going to shift over by 1 because you're on to the next bit. So that's what this means. Read bit index goes up by 1. Otherwise, if you're just in the saving input state, you know, read bit index will stay the same. And that's because of the fact that, you know, we'll have like 10,000 cycles where it's just staying the same value, and then that final cycle which it incremented. Otherwise, if we're in idle state or we're in the transmit key state, just set read bit index back to 0 so that next time we're in saving input, it'll start at 0. To compute the next value of the PS2 frame, when we're in the idle state, it's going to be 0. When we're resetting, it's going to be 0. But when in the saving input state, the next value of the PS2 frame is going to be the current value, and to insert the PS2 data shifted over to the left by read bit index. So we're inserting PS2 data at the read bit index spot. We can do that like so. Otherwise, just wait around while the PS2 clock has not risen yet. Okay, and then pulse new key when we're in the transmit state. And now we have a Verilog module which will construct a PS2 frame and do pulse when the PS2 frame is ready. And now we can use this module for our audio implementation by instantiating it here and taking the PS2 frame output and feeding it into a ROM, which will then map, well, first we want to take the frame and extract just the 8 bits that indicate the key, right? Because remember, we have 11 bits, start, stop, parity. We only care about these 8. Okay, so we're going to extract that 8 over here. That's the key code, I called it. And then we're going to pass that into a ROM. The ROM is simply a mapping from the PS2 scanset2 code to the key. Okay, so remember that's 8 bits with that table I showed you. That's what's on this side. And we're going to map that to what key I want to play, which is going to be the note. And then that note is going to be sent out of this module. And then there's some audio stuff which will play it. Also, I wanted to say quickly that integrated logic analyzers were super useful in this development process to see what the FPGA is seeing, because you can't do that in a test bench. But here, when we have this integrated logic analyzer the keyboard is able to, the FPGA is able to say, hey, the keyboard sent me these signals, and I currently have the wires and variables set at this and that, and send that back through the JTAG, which was super helpful for debugging. So now I want to talk about some extra complications and things like that to get this set up and working. Okay, so let's talk about another complication. You're probably wondering why I have a breadboard instead of just plugging in the PS2 clock and PS2 data straight into the FPGA. The answer is that I want to, well, there is actually two reasons. First, I need to use the pull-up resistors. But second, I want to make sure it's at 3.3 volts. Because if you look at the constraint file, I'm using LV CMOS 3.3 volts, which means that for the inputs here. So that means that these inputs expect it to either be at 0 volts for 0 or at 3.3 volts for 1, not 5 volts. 5 volts is too much, and I don't want it to be at the full blast of 5 volts to avoid frying this FPGA. The second reason is the way that PS2 clock and PS2 data are designed. The keyboard PS2 can only pull down the PS2 clock and PS2 data wires to 0 volts, but they can't actually pull them up. So what you need to do is have a pull-up resistor. So first of all, we have over here the voltage divider going from 5 volts to 0 volts so that the place where PS2 clock and PS2 data is at 3.3 volts, or their whereabouts. The way it works is when the PS2 clock and data wires and the FPGA both share this, they're both connected here. When the PS2 clock wants this to be a 1, it will just be hands off. And when it's hands off, or it's a Z, disconnected, then this voltage divider will make this 3.8 volts. However, and the FPGA will read a 1. However, when the PS2 clock wants this to be a 0, it will pull this down to ground, okay, using the ground that you fed it with the black wire. And then the FPGA will read a 0, okay? So that's how it works. It can't magically make, if we didn't have this, it wouldn't work because 0 would be fine, but when it's Z, that wouldn't tell you that it's a 1. You see, it can't actually pull anything up. All it can do is pull down. So that's why you need this, so that when this is disconnected, this reads as a 3.8. Now, the reason that they designed it this way is because the FPGA can also send signals, okay? And I'll get to that in a second. But when the FPGA, if the FPGA is sending a signal to keep this wire high, so if the FPGA wants this wire to be 3.3 volts, and the PS2 at the same time wants this to be 0 volts, you get a short, which would be really bad. But because it's pull down, this problem never happens. Because if the FPGA were setting this to a 1, it would simply be disconnected. And if the PS2 at the same time were setting this to 0, it would be grounded. But when this is disconnected, we can't have a short. So that's why they designed it this way. Now let me talk about the fact that the FPGA has to set this to low. So when I first bought this keyboard and I plugged it into the oscilloscope and I started hitting the keys and I was like, okay, let me see what happens. Nothing was working. It was just sending the hex code AA repeatedly. Every single second it was sending the AA hex code. And I was like, wow, this is so annoying. It turns out that this keyboard is one of the special keyboards that requires you to send a signal first to it when you turn it on saying, hello, I acknowledge you and I'm ready for you to send me signals. That's called sending the F4 hex code to enable scrolling. Before you do that, it will just assume that you're not ready yet and it'll keep sending AA hex code, which is the BAT, Basic Assurance Test. And so in order to get around that, when FPGA first turns on, you have to send the F4 hex code. Thanks for watching. I hope this was helpful for integrating keyboards into your own projects.